everyone. This is the last lecture of this week and of course of this course. So, what we have been doing, we have been just trying to understand some of the or introduce some of the features of finite element method. So, if you recall, these are the different kinds of elements that we discussed. We also discussed how to approximate these nodal variables through shape functions. Okay, how to construct those shape functions depending on the number of nodes you have, number of degrees of freedom you have. Okay, we also discussed the concept of convergence, that we can get to the actual results by either by reducing the number of or increasing the number of elements, and also we can get to the actual results by, or we can reduce the error by having shape functions with higher order. So, the first one is called H convergence and the second one is the P convergence. Okay. Now, that also we discussed. Now you see, if you recall this the shape function, this important thing, this if stiffness matrix is obtained by this, right, B transpose dB. Now, we also discuss what is we just name what is isoparametric element. The detail we have not discussed isoparametric element, but we mentioned that there is a way, if your elements are having different shape, we can always have a map between a square element or rectangular element which is defined in a parametric space, and then you have a map between that parametric space to the actual space, and then you can construct your shape functions, then integrations on the parametric space, keeping the map between the parametric and the actual space preserved. So, you see, this is the stiffness matrix, and also similarly in the load vector also you have an integration, right, if you recall. So, these integrations, very often it is not possible to have this integration in a closed form. We have done it for bar element, for beam, we have also done it for triangular element with 3-noded triangular element, but most of the cases this integration is not possible using closed form. Because of the nonlinearity associated with the model, though we are talking about only linear problem, because of the shape of the domain over which that integration is being done, and then you have a quadratic nature here. So, because of all these things, the integration may not be possible in a closed form. So, you have to look for some alternative technique. Then you might have studied various integration methods, like for instance, if you have a function, any function, suppose before coming to the wider technique that is being used in finite element method for integration, suppose I have a function, any function f x, which is defined over, say, between x is any function. If we take, this is a point and this is another point, this is defined over, say, this is 0 and L, and the function is, suppose, any function L. Now, I have to integrate this function between these 2 points, and this is the function. So, we have what we have to do is we have to integrate f x dx over, say, over this length omega. Okay, this is integration. So, if that we can have a closed form solution, we can also, due to this, for many functions this closed form integration may not be possible, then we go for numerical integrations, and some of the techniques that you have already studied in numerical technique. For instance, you might have studied trapezoidal rule. What is trapezoidal rule? Trapezoidal rule tells you that you divided this entire thing into small segments. You see, here also the concept is very similar. You divide the entire domain into small sum steps. If suppose these steps are d, for instance, if these steps are d, you can have equal steps, non-equal steps. If the steps are d, then for instance, in one dimensional case we can have this function as, so we can write f x dx integration over this, that becomes d by 2, then f1, suppose this is, and in between the value is, say, f1, this is f2, f3, f4, this is the function value at this point, this is the function value at this point, and so on. So, d by 2 plus f1 plus d into f2 plus d into f3 and so on. Then finally, we have that d by 2 into fn, right. And so, essentially this gives you summation of wi into fi, where fi are the function values at these steps, and then wi is essentially the weights associated with that particular point, right. So, this is how we have seen how to integrate like this. We have also seen Simpson's rule, for instance. The Simpson's rules also very similar to that Simpson's rule. The Simpson's rules here in trapezoidal rule, it is assumed that between these two your function is linear. This function is linear, then but you cannot have a linear functions. So, in Simpson's rule we can have a nonlinear, assume a nonlinear function, but even in Simpson's rule eventually we get function f(x) dx is equal to summation of wi and fi. How you construct this wi? The essence remains same, whether you use Simpson's rule, trapezoidal rule, that you are breaking into small segments and calculating the function values for each segments and multiplying it by some weights and then summing them up. So, depending on how you calculate these weights and how you divide the entire domain into small segment, there are different methods. Okay. The method that is used in finite element method, this method is Gauss quadrature method, right. Okay. This is the method very commonly used in finite element method. Gauss quadrature method tells you what? See, if you look at the other methods, whether the trapezoidal rule, Simpson's rule, as I said, you have several points. At every point, their weights are associated with those points. You calculate the function value at that point, multiply by their respective weights, and then sum them. From that perspective, Gauss quadrature technique is essentially also same. We have several weights, we have several points, and then you calculate those values at those particular points and multiply their weights. But you know, how to get those points and weights we are not going to discuss here. That is detail you might have done in numerical methods course, or if you see any numerical methods book, all the descriptions how to arrive at these points and their associated weights are given. So, in Gauss quadrature technique also we divide it into small weights. Okay, it is done. Suppose if we have a domain between -1 to 1, say -1 to 1, and if you have to integrate this between -1 to 1. So, location, so you have to what this technique tells you that you get a points either this point, or for instance you have -1 to 1, you take 2 points between this, say these points and these points, or you can have say 3 points. Okay. So, we have -1 to 1, you have 3 points and so on. So, these are 3 points. Okay. Now, when you have, so you want to integrate a function between this. So, suppose this is a function. Okay. This is a function. Now, what this tells you, you calculate the function at this point and then multiply it by their weight and you get the integration. Similarly, 2 point means you calculate the value at this point and at this point and multiply by their weight, sum them up, get the integration. Similarly, for 3 point integration. Now, what are those values? For 1 point integration, you have just one value n and associated weight is 2. And then for 2 point, for this case your weights, the corresponding coordinates of these points are 1 and associated is 1. And then for 3 point, the corresponding points are these and associated weights are this, and the summation of all the weights will be equal to 2, because in this case your domain, the length of the domain is 2. It is in one dimensional case. Similarly, in higher dimension you can have such Gauss points. These are called Gauss points. In higher dimension I am going to show you that. So, this is how you can, similarly for 4 point integration, you have the 4 points and then these are the corresponding weights, and if you sum them you will see that the summation of these weights are 2. Okay. Now, for instance, if I have to give you some example, suppose Suppose take an example, take the suppose fx is equal to say say integration over minus 1 to 1, okay, and then we have say 2 plus x square, okay, and then dx. Now, if we integrate it, if we closed form, if we integrate it, then the solution what we'll get is, we'll get 4.6667. Okay, this is the closed form solution of this integration. Now, let us do it for using Gauss quadrature technique. First, we use the 1-point Gauss quadrature, and then we'll see with 2-point Gauss quadrature. 1-point Gauss quadrature tells you that say I1 1-point Gauss quadrature, that is equal to, you calculate the values at x is equal to 0. Calculate the value. So, this gives you I1 is x I is equal to 0 and x1 is equal to 0 and w1 is equal to 2. So, then integration will be, integration I will be, that function is to be, it is at x is equal to x1 into w1. So, this becomes, if we substitute that, 2 into 2 is equal to 4. Now, you see actual integration is 4.68, but we get 4. Now, let us do it for, this is for 1 point, okay. Now, do it for 2-point integration. 2-point integration. 2-point integration is what? x1 is equal to 1 by root 3 and w1 is equal to 1, x2 is equal to minus 1 by root 3 and w2 is equal to 1. Then integration will be f of x1 into w1 plus f of x2 into w2. If you do that, you will get 4.6667, which is close to this. Okay. So, what point rule, what rule you apply, that depends on what is the function you are going to integrate. In general, if you are using n rule, suppose n is equal to 1 in this case, n is equal to 2 in this case, n is equal to 3 in this. So, if you have a polynomial, suppose in this case, if you integrate a polynomial whose order is p. So, in this case your for a constant p is equal to 1, for a linear function p is equal to for a constant p is equal to 0, for a linear function p is equal to 1, for a quadratic function p is equal to 2, and so on. So, generally n point rule can integrate a function of 2p minus 1, okay, 2p minus 1. So, if you are using n point rule, then it can integrate, it can gives you exact integration of a polynomial up to order 2p minus 1. Okay. For instance, in this case n is equal to 1. So, if I use first point into rule 1, n is equal to 1 point integration, then it can integrate. In order to get a linear function, suppose I have a linear function, then for linear function, what integration rule I have to use? 2 into 1 minus 1 means 1 point integration rule. But if you have a quadratic function, for instance, it is quadratic function, so we have to use So, yes, so 2n minus, no, it is not 2n minus 1, it is 2n minus 1, okay. This is 2n minus 1, okay. Okay. So, if your n is equal to whatever rule you have, so if you are using first rule, then first rule can integrate up to integrate a polynomial up to 2n minus 1. Similarly, if you are using second rule, then it can integrate a polynomial up to 2 into 2 minus 1, means up to cubic polynomial. Now, we have this quadratic polynomial, that is why with 2-point rule we got the results. Okay. So, similarly, now if we have if we have say if we have an expression like, if we have a triangular element, okay, like this, even in triangular element you can have a Gauss points, this is for 1 point, for a triangular element then you can have a Gauss point like this. So, these are for different rules. Okay. So, this is, we can have a Gauss point like this, these are called Gauss points. So, if you want to integrate a function over this triangular element, then this rule says that you calculate the value at this point, multiply by their weight. This point says that if calculate the value at these points and multiply by their weights and sum them up. So, similarly for rectangular element, for this kind of domain, we can have we can have a rule like this, or we can have a rule like this. We can have a rule like this 2.2 by 2 rule, and so on. Now, the thing is, we can have a rule like this, or say 3-point rule if you want to use. Then, so these are the 3 by 3 rules. Okay. So, depending on that, what function you are going to integrate over this domain, we have to choose the Gauss what rule of Gauss point, what integration rule you use. Now, you see here your Gauss points are, if you look at the previous slides. If you look at the previous slides, your Gauss points are already, it is between -1 to 1, right? That is what we it is always between -1 to 1, and if you have in 2 dimension, it is x -1 to 1, y -1 to 1. But at the end, at the end my element may not be as I said, element may not be a perfect rectangle, may not be a perfect square, but again we all the Gauss points are defined in a parametric space, and then we have a map between parametric space to the actual domain, and that map needs to be preserved. This is defined by that map, and that map needs to be put into the integration to get the integration over the actual domain with the information about the parametric domain. Okay. So, this is how the integration can be done in FEM. You see, though, if you recall, then there are 3 major things we have done. One is, okay, one is we have discretized the we have discretized the domain into set of elements, and then next thing is, this is called the domain discretization of the domain. Then next is we have done is, for every element we have an approximation of the field variable, and that approximation depends which kind of element we are using. That is called approximation of field variable, that step. And then once we have approximated the field variable, calculated the strain displacement relations and so on, we substitute that relation in that expression of in that expression of stiffness matrix, and then we get the stiffness matrix, and for the stiffness matrix we have to perform the integration. So, there are 3 major things. One is decomposition of the domain, the discretization of the domain, and then approximation of the field variable, and then finally integration. At every stage you have some error, you introduce some error into the formulation. For instance, at the domain decomposition stage, if you are discretizing a circular domain, for instance, suppose your domain is a circular domain. Now, if we want to discretize this circular domain with a triangular element or quadrilateral element, what you can do is, you can this exact domain cannot be, your discrete domain may not be an exact representation of the actual domain. In limited sense, yes, if you keep on increasing the number of elements, reducing the size of the elements, all this curved boundary can be closely approximated. But for that you have to, if you have to increase the size, you have to decrease the size of the elements. But even with decreased size of the elements, whatever formulation we have studied so far, that based on that we can say that even with that we introduce some error. That is, error is called domain decomposition error, and that error can be reduced by choosing smaller number of elements, right. Another thing is, second thing is the discretization error, approximation. At the approximation of field variable, we assume over each element your approximation linear or quadratic, but your approximation your actual solution may not be linear, may not be quadratic. It may be some higher error. It may be your solution may not be consistent with that approximation. So, there we introduce some error, and finally, at the integration stage, because you have to do integration numerically, that integration also we introduce some error. The total error will be the cumulative, or the total error will be the sum of all these errors, but there are ways to reduce all these errors. There are mathematical basis to quantify those errors that we are not going to discuss here. Now, finally, as a final remark, if you before we close, you see, as I started this week by saying, here in this week our objective is not to even introduce finite element method, because that is also not possible in just a week time. And whatever discussion we have made in finite element method, the discussion, we tried to make that discussion in line with the methods that we learned in matrix, in line with the philosophy of matrix method of structural analysis. We tried to view finite element method in the same way that we viewed matrix method of analysis. That is why in our discussion we portrayed, or we, as I said, we tried to understand finite element method as an extension of matrix method of structural analysis. Okay. So, that we did because that the objective here so that better comprehension can happen. But yes, as a finite element method it was started in 50s, and in the last 70 years time it has been extensively developed. It has a very sound mathematical basis. The errors can be proved. And today any branch of science and engineering, not even in science and engineering, everywhere, many places finite element method can be used. You see, there is two ways you can look at finite element methods. One is the ingenious way and another one is mathematician's way. Ingenious way, that just now we have studied, we have tried to see that. But then finite element methods is a method can be viewed as a numerical technique for solving partial differential equations, right? That is the mathematician's way. So, wherever you have partial differential equations, you can have a mechanics problem, you can have heat conduction problem, you can have electrical engineering problem, you have physics, chemistry, or even you have some other fields which are non-engineering or non-science field. There also you can have partial differential equation. Wherever you have that, yes, finite element method can be applied there. It is so huge, so vast. Okay. So, therefore, now, so as I said, the objective here is to open the door to tell you there is a method out there and which needs to be explored, and that is the finite element method. Okay, before we close, as a concluding remarks of the entire course, you see, this is the basic steps in engineering analysis. If you remember, these steps we discussed in one of the earlier classes of this week. We start with we have a physical system, we idealize the physical system and then write the mathematical model of that physical system, and then solve them and find out the solution of that. It is an example, the example is given like this. For instance, if you have a dam problem, this is the physical system, this is the idealized system, and this is the mathematical model for this physical system. In this mathematical model, we have three components. One is the governing equations here, governing equations here, then the definition of the domain over which this equation is valid, in this case it is omega, and then set of boundary conditions and initial conditions that describe the entire mathematical model, and then we solve it. Now, and this solution technique, this what we are studying, whether it is we are studying in structural analysis 1 or matrix method of analysis 1 or even in finite element, our main focus is essentially this step, how to solve this governing equation through different methods. And finite element method is a one method for solving this equation. Okay. Now, just to make our discussion for the completeness of the discussion, yeah, this is the thing. So, these equations can be solved either analytically or numerically. Analytical solution, most of the practical cases not possible. We have to solve it for numerically, and finite element is a numerical methods. The finite element, we discretize the domain into set of elements and then write the equations for each element, assemble them, get the solutions. There is another class of method which are called element free method, where we discretize the entire domain, but not into elements. We have a set of points and all the equations and everything writes based on those set of points, there is no element, and that class of method is called element free method. Okay. So, now even in this category, element based method and element free method, finite element is one element based method. So, in this category, element based method or element free method, again there are many such methods which can be coined, which can be put either in this broad category, either based on elements or which do not rely on elements. Okay. Now, before we close, you see, essentially when we talk about, there is a famous quote by mathematician George Box that all models are wrong, but some are useful. See, when we say a model, it's a very word model itself says that we are dealing with an approximate system, right? Right from the physical system to idealization, then writing the mathematical models of that idealized system, and then finally solving this mathematical model. At every stage, we assume something, right? Every idealization is based on, every step is based on certain assumptions, right? And therefore, and with every assumption, we slightly deviate from the actual system, right? So, the final solution what we get, that is not the solution of the actual physical system, rather the solution of the idealized system or the idealization that we have made throughout the process. Okay. In that sense, that then there is nothing like which one is right model or which one is wrong model, right approximation or wrong approximation. The very word approximation tells you it is not right, it is not the actual thing. What is important is whether that approximation is useful or approximation is not useful. Whether some approximation, whether some method is useful or not, that depends, that you have to decide based on what information you want to extract from the analysis. What is the purpose of the analysis? What is the outcome of the analysis, how the structure or any object may behave under certain circumstances, what kind of behavior we are expecting from the analysis, from the structure. Depending on that, we have to choose a numerical methods, right? So, now this is the starting point that you will be. It is the first step towards first step towards finite element method, and as you learn finite element method, we will also see there are different branches in finite element method. Branches in the sense different way you can enrich the basic formulation of finite element methods. Then there are methods which do not rely on elements, and even in that category there are hundreds of methods. Okay, every method has their own advantages and disadvantages. Now, depending on your requirement of the requirement from the analysis, you have to see which method will be useful for you. And with this, I stop here today and close this entire course. So, with this, thank you, and I believe that you have enjoyed the entire journey. As in the beginning of every lecture, we show you the front slides where our email IDs are given. If you have any doubts, any confusion you want to ask, you want to interact, you are most welcome to write to us. With this, thank you very much.